In this lecture, we are going to discuss very briefly about the X-rays. We will discuss that how X-rays produce, what is X-rays, and how X-rays are produced. What are the types of X-rays, and what is a practical application of X-rays? Dear student, X-rays are a type of electromagnetic radiations whose wavelength lies between the wavelength of ultraviolet radiations and gamma rays. So we can define X-rays as X-rays are electromagnetic radiations whose wavelength lies in the range of lies in a range of between ultraviolet radiations and gamma rays. So X-rays basically lies in the wavelength of UV radiation. Their wavelength is between a UV radiations X-rays and gamma rays. Gamma wavelength. This student, please keep in mind that let me write this clear. Gamma rays wavelength. This student, please keep in mind that the UV ray radiations have a wavelength, and their wavelength is in a range of it is in a range of 100 nanometer to 400 nanometer. So it is between 100 nanometer and 400 nanometer, whereas the wavelength of X-rays is around zero point 0.1 nanometer to 10 nanometer, or we can say its wavelength is around 1 angstrom to 10 nanometer. Whereas the wavelength of gamma rays, it is very short. The gamma radiations are very short, and their wavelength is in the range of 0.1 nanometer to 10 raised to power minus 12 meter. So this is very shorter wavelength as compared to the ultraviolet radiation and as well as X-rays. So X-rays are electromagnetic radiations whose wavelength lies between ultraviolet radiations and gamma rays. These are, since the wavelength of X-ray is very short, so due to this, the X-rays are known as high energetic radiations. Now, students, what do you think how X-rays are produced? X-rays production is a reverse phenomenon of photoelectric effect. In photoelectric effect, highly energetic photons are basically incident on the surface of a metal. Consider this is a photon and this is a schematic representation of a surface of a metal. Since you know that electrons reside on the surface of a metal, and in photoelectric effect, a photon of beam of highly energy is incident or fall on the surface of a metal. And this photon beam basically remove the loosed electron from a surface of a metal like this electron. So basically, in this phenomenon is known as photoelectric effect. Photoelectric effect. So basically, in photoelectric effect, the energy, the total energy, and as well as momentum is basically of momentum of a photon is transferred onto the surface of a metal, and when this energy, total energy of photon, is transferred on the surface to the surface of a metal, if the energy of photon is higher than the binding energy of electron present on the surface of metal, then this highly energetic photon will basically release electron. Whereas in a case of X-rays, it is reverse to the photoelectric effect. In X-rays, highly energetic electron, suppose that this is an electron. So in X-rays production, highly energetic electron is basically fall on the surface of a metal. Consider this as a surface of a metal. So as you know that surface of a metal have a bounded electron. So when this highly energetic photon electron incident on the surface of a metal, they will result into production of highly energetic radiation, and these electromagnetic radiation produced are known as X-rays. X-rays. So dear student, X-ray production is a reverse phenomenon to the photoelectric effect. In photoelectric effect, highly energetic photon is incident on the surface of a metal, which cause ejection of electron from the surface of a metal. Whereas in X-rays production, highly energetic X-rays are basically incident on the surface of a metal, and they, due to high energy of electron, they basically cause some kind of physical phenomenon. They may cause a de-acceleration of incident electron, or there may be occur an inner shell transition, and due to this, radiation produced will be X-rays. And keep in mind that the interaction of an electron with the surface of metal, there will be two ways of interaction of electron with a surface of a metal. One way, electron may interact with the surface of a metal, may cause an inner shell transition. And in second way, electron interacting with the surface of metal, there could be a possibility of de-acceleration of this incident electron. So due to de-acceleration or inner shell transition, there is a possibility of a generation of electromagnetic radiations known as X-rays. So dear student, keep in mind that there will be two types of interaction. One type interaction of electron with a surface of metal is known as inner shell transition. Whereas second type of interaction which is possible for electron, second types of interaction which is possible for electron to do with the surface of metal is known as de-acceleration of electrons. De-acceleration of electrons. Now, student, please keep in mind that due to the inner shell transition and as well as de-acceleration of electron from the metal surface, they basically cause a generation of two types of X-rays. X-rays which are produced due to an inner shell transitions are known as characteristic X-rays, and whereas X-rays which are produced due to deceleration of electron, such types of X-rays are continuous X-rays, and these X-rays are also known as Bremsstrahlung radiation. Bremsstrahlung radiations. So now let us discuss inner shell transition in brief. Inner shell transition in brief, and let us discuss that how due to inner shell transition characteristic X-rays are produced. Since you know that the student, an atom consists of a nucleus. Consider the atomic structure. This is atomic structure, and we have an atom, and this is a nucleus of an atom, or it is a schematic representation of a nucleus of an atom. And in every nucleus of an atom, according to Bohr atomic model, there are energy level present around the nucleus of an atom, and these energy levels are known as shell. First energy level around a nucleus is known as K shell. Second energy level present around a nucleus is known as L shell. And similarly, third energy level present around a nucleus is known as M shell. L shell and M shell. So there are present different types of energy level around the nucleus of an atom, and these energy levels have electrons present in it. Suppose that this is a schematic representation of an electrons present in these energy levels. So this one, keep in mind that the energy of electrons in each energy level is same. However, energy of electrons in different energy levels is different. This is a schematic representation of a sodium atom. So sodium atom has 11 electrons, and these electrons are present in energy levels. And the first energy level of sodium atom is known as K shell, and it has 2 electrons, whereas the second energy level is known as L shell, and it has 8 electrons, whereas third energy level of sodium atom is known as M shell, have 1 electron. So now every energy level have a specific energy. K shell have lesser energy. K shell have lesser energy than L shell, and L shell have lesser energy than M shell, which means that higher energy level electrons have higher energy than the lower energy level electrons. So now, whenever highly energetic electron is incident on electron present in energy level near an atom, and suppose that this is a highly energetic electron and it is incident on the electron present in an inert energy level. So if the energy of this incident electron is higher than the binding energy of electron which bound electron in this energy level, then this incident electron will cause ejection of the electron which is present in a ground state. So electron will basically eject it due to incident of the incident electron, an electron will be ejected and it will move outside or move away from the atom. And similarly, the electron which is incident, it will be deflected and it will also basically move away from an atom. And so the color of this electron is yellow, so we'll make it yellow. So now the incident electron causes the ejection of electron in which is present in inner shell, and similarly it is also deflected, so there will be this inner shell will have one electron less. There will be generation of vacancy. There will be generation of vacancy in vacancy vacancy. There will be a generation of vacancy in a K shell. So this means that when there is a vacancy in a K shell, innermost shell, this means that the structure of an atom is unstable. In order to make this structure of an atom stable, the electron from L or M shell will jump into the vacancy of the K shell. And whenever electron from higher shell like L shell and M shell jump, they will cause generation of characteristic X-rays. So now, suppose that electron from this K shell jump into the vacant position of an L shell. So whenever electron jump from K shell into L shell, these electrons will release electromagnetic radiations in a form of X-rays. Now, question here is that why the electron when jump from L shell to K shell produce X-rays? The reason is quite simple, that the electron at the L shell have higher energy than the electron which is present in a K shell. The L shell have higher energy than the K shell. In order for electron to jump from L shell into K shell, electron require to remove some amount of energy. And whenever the energy of L shell electron reaches to the energy of K shell electron, then in that situation electron from L shell will jump into a K shell. So that is the reason, due to jump of electron from L shell to K shell, they will release electromagnetic radiations known as X-rays. So the jump of electron from higher energy level to a lower energy level is known as inner shell transition. And due to the inner shell transition, there is a generation of radiations, and these radiations are known as characteristic X-rays. So dear student, please keep in mind that there could be different types of X-rays produced due to characteristic X-rays may be produced due to inner shell transitions, and these characteristic X-rays are known as K alpha, K beta, K gamma, L alpha, L beta, L gamma, M alpha, M beta, and M alpha, M gamma, and so on. So the type and nature of X-rays will basically, characteristic X-rays will depend on the number of shell or on the type of energy level from which there occurs an inner shell transitions. On the basis of that, there are different categories of characteristic X-rays which may be produced due to inner shell transitions. So dear student, now let us discuss about the deceleration of electron, which is basically causing a generation of continuous X-rays. Since you know that an atom has a nucleus, again we are considering an example of a sodium atom. Consider this is a nucleus of sodium atom, and sodium atom has 2 electrons which are present in first shell, and similarly it has 8 electrons which are present in second shell, and similarly it has one electron which is present in a third shell or third energy levels. So suppose that these are the two electrons which are present in a first energy level of sodium atom, which is known as a K shell. Eight electrons, one, two, three, four, five, six, 7, and eight electrons which are present in second energy level or L shell, and one electron which is present in M shell or third energy level. So now, as you know that X-rays are produced whenever highly energetic electron fall on the surface of metal atom or fall on the metal atom. So here, suppose that this is highly energetic electron, and this there could be a possible of interaction, different types of interaction possible with the atom, with the surface of atom. This electron, incident electron, may be passed closer to the nucleus, and since you know that in nucleus there are protons, so this electron may be deflected by a nucleus of an atom, like that deflection. So, whenever an electron of higher energy is incident on the atom, and since you know that nucleus of an atom is positively charged and electron is negatively charged, whenever this electron incident on the nucleus of atom may cause the deflection of electron because of the force of attraction between a nucleus and electron, and due to deflection of electron there will be a release of energy in a form of radiation, which is known as continuous X-rays. Continuous X-rays. So now the question here is that why continuous X-rays are produced, since you know that incident electron have a specific speed and energy and momentum, and whenever it is passes through the nucleus of near the nucleus of an atom, there will be an interaction of a positive charge nuclei with the negatively charged electron. So this interaction will basically cause a change in a speed or a momentum of an electron, which cause a deflection, and due to change in speed or momentum the energy of the incident electron change, and this transfer energy is basically appeared in a form of electromagnetic radiations known as continuous X-ray. So dear student, please keep in mind that in inner shell transition, electron from higher energy to a lower energy, basically suppose that we have these energy level. This is ground energy level E1, this is slightly higher energy level E2, and this is further high energy level E3. So in inner shell transition, electron from higher energy level E2 jump into E1, and they release energy in a form of electromagnetic radiation, which is known as characteristic X-rays. Similarly, from this high energy level E3, electron jump into E1 and they release electromagnetic radiations in a form of X-rays. And the energy of this electromagnetic radiation was basically, it was a change of E2 minus E1, which was an energy of the X-rays. Similarly, energy between 2 and 1. Similarly, energy E third transition state to 1 was basically E3 minus E31. That was energy difference, which was basically creating a characteristic X-rays due to an inner shell transition. Whereas characteristic X-rays, whereas in case of continuous X-rays, the electron have a specific energy and momentum, and they have a specific energy. So whenever they pass through a nucleus have a positive charge, so they basically will increase, they will basically change the initial energy of electron which is incident on an atom. And due to change in initial energy and a momentum of electron, there will be a release of energy, and that release of energy is known as continuous x-rays. So basically these are the two types of interaction. One is the inner shell transition, and second interaction is the deacceleration of electron, which are basically producing characteristic and as well as continuous x-rays. So now let us discuss about the experimental setup used for the production of setup used for the production of X-rays. It was a German physicist known as Roentgen who discovered X-rays. Roentgen produced X-rays in a glow discharge tube which consists of two metal electrodes, and these electrodes were known as cathode and anode. And by applying a higher potential, Roentgen observed new type of radiations produced on the surface of a metal known as cathode, and he gave that new types of radiation name as X-rays because the nature of these discovered radiation was unknown. So now let us discuss that how and what type of experimental setup Roentgen used in a discovery of X-rays. Dear students, X-ray, the experimental setup used by Roentgen consists of a glow discharge tube. This glow discharge tube was basically a highly evacuated vacuum tube. It was basically made up of a Pyrex cloth. It was a vacuum tube, and this vacuum tube was evacuated by connecting it with a vacuum pump. So any unwanted material present in a tube was basically removed by a vacuum pump. The pressure inside the glow discharge tube was maintained around, the pressure was basically maintained around 10 raised to power minus 10 raised to power minus 6 to 5 into 10 raised to power minus 8 atmos, or it was in the range of 0.1 to 0.005 Pascal. So now let me clean this. Dear student, Roentgen used two types of electrode inside this vacuum glass tube or inside the glow discharge tube. One type of electrode is known as cathode. Whereas second type of electrode present inside a glow discharge tube was anode. Cathode and anode were used in a glow discharge tube in experimental setup for the production of X-rays. Cathode anode was basically made up of element or metal of heavy metal, and basically there were different types of metal used. However, most commonly molybdenum, Mo, or tungsten was used for the production of X-rays. We will discuss later on why molybdenum metal was used in a production. Molybdenum, heavy metal like molybdenum or tungsten was used in a production of X-rays. Dear student, please keep in mind that these electrodes, positive cathode and anode, were basically connected with high potential source battery, and that battery basically operate at very high voltage. This is negative terminal of the battery, and whereas this is a positive terminal of the battery. So basically the anode cathode is an electrode. It is connected with a negative terminal of the battery, and whereas anode is a positively charged electrode which is connected with a positive terminal of the battery. Dear student, please keep in mind that usually the of uh, cathode present in a glow discharge tube is connected. Usually, it is connected with it is connected usually with a filament. Usually, it is a tungsten filament which is used to heat tungsten filament which is used to heat the tungsten filament which is used to heat the cathode in order to generate highly energetic electron beams or electrons. So Roentgen applied voltage around 30 kiloelectron volt to 50 kiloelectron volts, and he observed that whenever he applied a voltage in a range of 30 kilo electron volt to 50 electron volt, there was a release of highly energetic electrons from cathode, and these electrons from cathode incident on the surface of an anode metal. And these electrons, since the voltage was quite high, the electron which were basically produced by the cathode have very high energy. And whenever you observe that when these highly energetic electrons fall on the surface of metallic anode, they release a new type of electromagnetic radiations, and these new type of electromagnetic radiations were are known as X-rays. Now, the name of X-rays is quite interesting. It was because the nature of these new type of electromagnetic radiation was unknown. Due to this, these radiation produced due in a glow discharge tube were basically called unknown radiations or X-rays. Student, please keep in mind that whenever the electron from cathode with high energy fall on the or incident on the surface of metal, in order to produce electromagnetic radiation in a form of X-rays, the binding energy of the electron which are present at anode must be less than the energy of incident electron. So they will basically cause a generation of they will cause in if the binding energy of anode electron present at anode atom is less than the energy of the incident electron, then they will basically cause an inertial transition in anode metal, and due to this they will result into generation of a characteristic X-rays. In other case, the electron incident electron may be deflected from the inside the atom near the nuclei of this metal atom, and they can also cause generation of novel type of radiation, electromagnetic radiation known as continuous X-rays. So in this way, basically, with this experimental setup, X-rays are produced from the surface of anode metal. Now, interesting question here is that why molybdenum, heavy metal like molybdenum or tungsten, is used as an anode. Dear student, please keep in mind that atomic number of molybdenum is 42, which means that it is a heavy atom. So since the energy of this incident electron is quite high, and the incident electron is quite high, so it requires a stable atom which can basically hold the energy of incident electron. So due to this, heavy metal atoms are used in production of X-rays. Now, student, please keep in mind that the energy of incident electron is quite high. So in X-rays instrument, usually there are also used a cooling setup just behind the anode to cool the anode. Usually cooling water is used behind the anode, and they will basically also cool down the heavy metal anode. So that is a basic reason due to which heavy metal like molybdenum or tungsten are used as an anode in X-ray production. There are basically two types of theories present about the production of X-rays. One type of theory is known as classical theory, and whereas second theory of for the production of X-rays is known as quantum mechanical theory. Quantum mechanical theory for the X-rays production. According to classical theory of X-ray production, whenever electron from highly energetic cathode, highly energetic electron from cathode fall on a heavy metal anode, there will be a production of X-rays, but the production of X-rays classically it will be continuous. Whereas quantum mechanical theory said that the electron which are incident from cathode on anode, they release X-rays, but these X-rays are not continuous. They are in a form of discrete form of energy, and that theory is known as quantum mechanical theory of X-rays. Then please keep in mind that whenever electron fall on the surface of metallic anode, they release X-rays, but these X-rays are in a form of continuous plus characteristics. These X-rays are continuous plus characteristic X-rays. They basically never release continuous or characteristic X-rays separately. So both these quantum mechanical theories and as well as classical theories are applied in a production of X-rays. So basically the graph, in reality, the graph which are produced in a production of X-rays between wavelength and intensity, wavelength and intensity is represented as like this. K alpha X-rays and K beta X-rays. So basically, dear student, we observe two different types of peaks or many different types of peak in a production of X-rays like K alpha, K beta, K gamma, L alpha, L beta, sorry, L beta, L gamma, and so on. And these peaks, which are K alpha, K beta, and so on, these peaks cannot be explained on the basis of a classical theory, because classically it is said that X-rays are basically are continuous radiation which are produced by due to a bombardment of electron on the surface of anode. But in reality, there are a production of some additional peaks like K alpha and K beta. These K alpha and K beta and so on peaks are explained on the basis of quantum mechanical theory, which is known as quantum mechanical theory for X-ray radiations. Listen, please keep in mind that why these K alpha and K beta radiations peaks cannot be explained classically. According to Bohr atomic model, atoms have energy levels or shells, and these energy levels or shell have associated specific amount of energy. So electron present in these shells, they have discrete amount of energy in every shell. So the K alpha and K beta radiations are produced due to these energy level or inner shell transition of these energy level. Due to this, the K alpha and K beta radiations have a specific quantized energy. And that is the reason we cannot explain these K alpha and K beta classically, but they are explained on the basis of a quantum mechanical theory. So basically, a classical theory is old conventional theory, but the quantum mechanical theory is a modern theory which explain on the basis which explain these K alpha and K beta X-rays on the basis of inner shell transition, because every shell have a quantized energy. So the K alpha and K beta X-rays have quantized energies. In case if we want to explain X-rays classically, then the relation, the graph between intensity and wavelength and intensity must be somehow continuous like this. But in this is continuous. But in reality, it is not possible because there is inertial transition whenever electron incident on heavy metal anode, and there is not only deceleration but transition. Due to this, additional peaks will always appear in the form of characteristic X-rays. So now, student, please keep in mind that this shortest wavelength is basically known as cutoff wavelength. And cutoff wavelength is the shortest wavelength of X-rays. And in cutoff wavelength, the energy of X-rays, cutoff wavelength, the energy of X-rays is too much. So the cutoff wavelength is inversely proportional to the energy. Higher will be the energy of X-rays whenever this cutoff wavelength is shorter. So, dear student, please keep in mind that cutoff wavelength, which is this one, it's depend on the energy of accelerating electron, or it's depend on accelerating voltage. Whenever accelerating voltage is more, if the accelerating voltage is more, the cutoff wavelength will be cutoff wavelength will be short. Okay, and this means that energy will be more. So it is not depend of wavelength do not depend on a nature of material. However, though if we increase a voltage of a material, the K alpha peak and K beta peak, the position of K alpha and K beta peaks will never change. However, the position of these characteristic K alpha and K beta will only change if the type of material change. Like we change a material from molybdenum to tungsten, then the position of K alpha, K beta at a specific voltage will change. But the K alpha and K beta never depend on applied accelerating voltage. This means that cutoff voltage, cutoff wavelength, which is for continuous X-rays, depend on applied accelerating voltage, whereas the K alpha and K beta peak, basically, which is characteristic X-ray radiation, they do not depend on applied voltage, but they depend on the nature of material. Every material like molybdenum, tungsten, etc., they have a specific wavelength or specific peaks for at a specific wavelength for K alpha and K beta radiations. So this means that continuous X-rays depends on accelerating voltage. Depends on accelerating voltage. Whereas discrete X-rays, or which are known as discrete X-rays, which are known as characteristic X-rays, do not don't depends depends do not depends on accelerating voltage, but they depend on but depends on nature of material. Which mean that K alpha, K beta, K gamma, etc. characteristic X-rays, they basically will shift or change. Their position will basically shift or change in if the nature of nature or type of material, basically, or types of materials change. So the position of K alpha, K beta radiations for molybdenum, MO, and as well as tungsten will be different. So now let us explain briefly about the types of X-rays. Types of X-rays. There are two main types of X-rays. First type of X-rays is known as continuous X-rays. And second type of X-rays is known as characteristic X-rays. So now let us discuss continuous X-rays. Continuous X-rays are X-rays which are produced whenever a highly energetic electron incident on an atom, and near the nucleus of atom they get deflected. So due to deceleration of incident electron caused by nucleus and an atom, an energy in a form of radiation produced is known as continuous X-rays. So in continuous X-rays, basically, the student, consider this is an atom. Suppose that we said this is a sodium atom, and sodium atom has energy level like shell around it. This is first energy level. Suppose this is second energy level of sodium atom, and this is third energy level of a sodium atom. And electrons are present in these energy levels. In these specific energy level, 2 electrons are present in first energy level. Suppose that we write it N represent as nucleus of sodium atom. 8 electrons are present in second energy level. 1, 2, 3, 4, 5, 6, 7, and 8. Whereas 1 electron is present in last energy level, which is known as M energy level. So whenever a highly energetic electron, suppose this is an electron, this is electron and it has very high energy. So whenever it's fall on the sodium atom or on the atom, and when it's reached near the nucleus of an atom, the nucleus basically have a positive charge. So this positive charge and negative charge of electron, they will cause an interaction, and due to interaction the electron basically is deflected near the nucleus of the atom. So this deflection basically cause a generation of electromagnetic radiations, and this electromagnetic radiation is basically known as continuous X-rays. These types of electromagnetic radiations are continuously produced whenever electrons are incidented on the surface of metallic atoms. Continuous X-rays are produced by a phenomenon due to a phenomenon known as Bremsstrahlung process. Or continuous radiations are also known as Bremsstrahlung radiations. Bremsstrahlung radiations are electromagnetic radiations which are produced due to the acceleration. So the word Bremsstrahlung is a German word which means braking, which mean braking. Braking mean stopping. So these are basically radiations are produced due to deceleration or due to stopping or due to decrease in an acceleration of incident electron when they pass through a nuclei of an atom. In case of continuous X-rays, the radiation, the graph between wavelength and as well as intensity of X-rays must be like this. That represent a continuous X-rays. However, actual graph of intensity and as well as wavelength is like this. This is wavelength, this is intensity. Actual graph is like this. We have a peak, additional peak, and these peaks are basically represent a discrete energy level or present an inner shell transition, which are basically causing a generation of characteristic X-rays along with. So basically X-rays are a combination of Bremsstrahlung radiations. Actual X-rays produced are a combination of Bremsstrahlung radiation plus discrete or characteristic X-rays. We can calculate the cut-off wavelength. We can calculate the cut-off wavelength for the continuous X-rays. Since you know that energy E is equal to H into nu. E is equal to H into nu. Whereas potential to bring a charge is equal to work done by a unit charge. And we know that E is equal to Q into V, which means that charge is electron, so E is equal to EV. Suppose that this is equation number 1 and this is equation number 2. So we can combine these two. EV is equal to H into nu. Frequency, you know that frequency is inversely proportional to wavelength. If nu is equal to C by lambda, so this equation number 2 will become EV is equal to Hc divided by lambda, and lambda will be equal to Hc divided by E into V, and lambda is basically it is a cut of wavelength, which is equal to Hc divided by E into V. So this is all about a continuous X-rays. These are basically produced due to de-acceleration of electron whenever electron basically incident on high atomic weight metal, and they basically the de-acceleration basically cause a generation of a new types of radiation, and these radiations are produced in a continuous fashion, and these are known as continuous or breaking X-rays. So dear student, now let us discuss about the characteristic X-rays. Characteristic X-rays. Characteristic X-rays are a type of X-rays which are produced whenever electron jump from a higher energy level to a lower energy level in an atom. They are released due to inertial transition. They release electromagnetic radiations in a form of X-rays, and these X-rays are known as characteristic X-rays. So basically, in characteristic X-rays, there occur an inner shell transition. This inner shell transition occur due to the incidence of high energetic electron from a cathode onto the surface of a metal anode. The electron from the highly energetic electron beam from the cathode basically knock out electron of an atom of anode, and the knock out electron basically cause a vacancy in the inner shell of an atom of anode, and that vacancy is filled by electron jumping from a higher energy level into the vacant position of lower energy level, and due to a jump they basically release an energy in a form of radiation, which is known as characteristic X-rays. So now, dear students, let us discuss characteristic X-rays generation for molybdenum atom. Dear student, since you know that the atomic number of molybdenum is 42, MO has atomic number 42. Whereas the mass number of molybdenum atom is 95.94, which means that molybdenum atom has 42 protons, it has 42 electrons, whereas molybdenum atom has 54 neutrons. So we can basically represent molybdenum atom, the structure of molybdenum atom with a schematic diagram like this. Suppose that this is a nuclei of a molybdenum atom, and we represent it with an N. Nuclei of molybdenum atom have 54 neutrons and 42 protons. And on the nuclei of molybdenum, there are energy levels, and these energy levels are known as shell. First energy level of molybdenum atom have 2 electrons, because this is a representation of electron. Second energy level of molybdenum atom has 8 electron and it is known as L shell. So it has 8 electrons. 2, 3, 4, 5, 6, 7, and 8. Third energy level around a molybdenum atom is known as M shell, and this M shell has 18 electrons. This M shell, let me clean this. M shell, this is M shell, KLM, and it has 18 electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. So it has 18 electrons. And the fourth energy level around a molybdenum atom, this is a fourth energy level around molybdenum atom, which is basically O shell, and it has basically 13 electrons. So we can draw them as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13. Whereas the fifth and last energy level around the molybdenum atom is this. This is a last energy level around a molybdenum atom, and this last energy level of molybdenum atom have 1 electron. So suppose that this is 1 electron. So now, how different types of characteristic X-rays like K alpha, K alpha, K beta, K gamma, L alpha, L beta, etc. are produced from a molybdenum atom. Suppose that we have this energetic beam of electron, or we have this is a high energy electron. This is high energy electron. So now whenever this high energy electron fall on electron present in inner shell of an atom, suppose that this electron fall on electron present in a K shell of an atom, of a molybdenum atom, like this, and this electron basically knocked this K shell electron, knocked it out. So this basically will create a vacancy. This will basically create a vacancy in a K shell, because the electron from the K shell is knocked out, and the incident electron is also deflected, and it will go away from atom like this. So this incident electron. Okay, so now this incident electron, when fall on the inner shell, they create a vacancy in an inner shell. So now this vacancy basically will cause a molybdenum atom to become unstable. In order to make this molybdenum atom stable, electron from high energy levels, like, as you know that around the atom there are energy level. First energy level is known as K shell, second energy level is known as L shell, third energy level is known as M shell, fourth energy level is known as N shell, and fifth energy level is known as O shell. So basically electron in a K shell is ejected, so the K shell has a vacancy. So the structure of atom become unstable. So this vacancy can be filled by electron present in K shell, L shell, M shell, and N shell. If the electron from this L shell jump into a K shell, like suppose this electron jump into a K shell from L shell, then the jump of electron will basically cause, since the energy of electron at the K shell, at the L shell is higher than the energy required for electron to come into an K shell. So the higher energy of L shell electron will basically, they will give this extra amount of energy, and after giving the extra amount of energy they will jump into K shell. So in the meanwhile, the electron jumping from L shell into K shell, they will release electromagnetic radiations in a form of radiations known as K alpha radiations. So K alpha X-rays. So K alpha X-rays are produced whenever electron from L shell jump into K shell. So electron from L shell, suppose this L shell, electron present in L shell, whenever it jump into a K shell, electron will release electromagnetic radiations in a form of K alpha X-rays. So now, interesting question here is that if electron from M shell jump into a K shell and fill the vacancy of K shell electron, then it will also release X-rays, and these X-rays are known as K beta X-rays. So in K beta X-rays, electron from M shell, basically they jump into K shell. So suppose that this is electron which is present in M shell and it's jump into K ground shell, they release X-rays, and these X-rays are known as characteristic K beta X-ray. Similarly, dear student, K gamma X-rays are produced. In K gamma X-rays, electron from N shell jump into K shell. Suppose that this is N shell. An electron present in an N shell will jump into a K shell. And whenever this electron jump from N shell into K shell, they will release characteristic X-rays in a form of radiations which are known as K gamma X-rays. Similarly, dear student, L alpha X-rays are produced. L alpha characteristic X-rays produced. In L alpha characteristic X-rays, electron from M shell basically jump into a L shell. Electron whenever jump from M shell into L shell, they will release characteristic X-rays in a form of L alpha X-rays. And similarly L beta, L gamma X-rays are characteristic X-rays are produced due to inner shell transition. So in this way, basically, the student, characteristic X-rays are produced from. This is all about X-rays. X-rays are produced in a glow discharge tube or in a cathode rays tube whenever highly energetic electrons are basically incident on the surface of a metallic anode, and they release due to interaction, they release highly energetic X-rays in a form of characteristic and as well as continuous X-rays. Characteristic X-rays are produced due to an inner shell transition, whereas continuous X-rays are produced due to a deceleration of electrons. Due to inner shell transition, there could be a production of different types of X-rays like K alpha, K beta, L alpha, L beta, L gamma, uh, etc. So this is all about X-rays. So thank you for watching this lecture.